Well, hello and welcome to the webinar, LIS technology or LIS technology, the new way of ceramic 3D printing. My name is Madeline Pryor and I will, as always, be the moderator today. I am actually joined today by our distinguished panelists, Dr. Johannes Homer, Dr. Thomas Mueller, Dr. Holger Wampers, and actually we will also be joined as well, more for the Q&A session, by Dr. Stefan Walter, who is going to help especially with the more technical questions. Speaking of, please do note that there is a Q&A box at the bottom of your screen. Any questions you have, please do just ask them there. It will mean that it's much more likely that we see them. And if we could just move to the next slide. I will introduce myself and the speakers in a tiny bit, but before we get started, I actually wanted to send you as well a poll. If you would just take a moment, well, I will relaunch the poll. If you already answered the poll, if you could answer it again. It's just been launched one more time. Just please answer the poll and get the answers. Again, if you already answered it, please just do it one more time because it will delete it otherwise. Well, you see it on your screen. I see you're starting to answer. This is just to get an idea of who you are and what you're aiming to get out of the webinar today, so we can better understand what, who you are, since we cannot see you. I will leave you a few moments just to get that answered. Please do answer it. Additionally, just to let you know, we are recording this webinar. It will be available later on YouTube. If you would like to be notified of this, you can subscribe to the 3D Natives YouTube channel. We have a lot of other interesting 3D Natives content, as well, of course, the webinars, including this one. That will be in a few days. It will not be immediately afterwards. And while I'm just waiting for people to finish, I'm actually going to introduce the agenda. You can see on this slide that this is the agenda for the next hour or so. Right now, we are clearly in the introduction, and I will shortly introduce you to the panelists as well. Afterwards, we will actually turn into looking at the differences between LCM, which is the classical, the classic Lithoz technology for ceramic 3D printing and how it differs from this new technology, LIS, which is very exciting. And after that, you can learn more about the potential of the technology before we turn to some use cases and, of course, the Q&A at the end. Once again, please, just a kind reminder to fill in the Q&A at the bottom with any questions you may have. You'll be able to see the questions and also upvote any questions that you would like answered. I think we got the majority there, so I will just end the poll as well, just quickly. Very interesting. Many of you are in the ceramic industry actually, but we also have a lot of beginners, so a nice mix. And you're using 3D printing for prototyping, and you are hoping to get a deeper understanding of LIS. If you actually look, you can just see the answers on your screen right now. Well, you'll certainly get that, and we're excited to bring you with this today. So now to the panelists. As I previously stated, my name is Madeline Pryor. I am the English content specialist for 3D Natives, which is the largest online media platform on 3D printing and is available in 4 languages: English, French, German, and Spanish. Sorry, a 5th language, actually, Italian. I am the moderator of the panel and the Q&A, though I will mostly leave the talking up to these gentlemen here. Actually, let's start with the panelists. First up is Dr. Johannes Homer, who is the CEO of Lithoz. He has spent many years of research at Vienna University of Technology, which equipped him with the extensive technical knowledge of additive manufacturing of high-performance ceramics. He holds a PhD in material science and has worked in AM since 2003. In 2011, he co-founded Lithoz as a spin-off from TU Vienna, and as an expert in ceramic AM, he has written many publications and is also a co-inventor of numerous patents in the field. We are very excited to have him with us. Next, we have Dr. Thomas Mueller, who is the CEO of QEP3D. He has more than 14, he has a lot of experience in the industry because more than 14 years ago, he started with the development and process optimization in ceramic 3D printing for water-based slip systems at the TU Clausthal. Apology, German speakers, I will butcher everything. Dr. Mueller is involved in a number of publications and is the co-inventor of several patents in the field of ceramic 3D printing. Next up, Dr. Holger Wampers is the managing director at Alumina Systems. He completed his doctorate in the field of technical ceramics and has been working for many years in various responsibilities in the field of technical ceramics, including dental ceramics, mechanical engineering, soldering technology, or 3D printing. He has been the managing director of Alumina Systems for 11 years now and has integrated and has been very active in the group. And last but not least, our guest, who will come mostly at the end of the webinar, Dr. Stefan Walter, is the head of product and process development at Alumina Systems. He obtained his degree in material science from the Friedrich Alexander University in Erlangen, and he spent his postdoc at the University of Trento in Italy, doing research in the field of sol gel-derived glass ceramic materials. From 2001, he was working with corporate technology at Siemens in Munich in different topics like high temperature and ultra high temperature materials development, as well as high temperature application of ceramic matrix composites. Since 2021, he has been the head of product and process development at Alumina Systems and coordinates the additive manufacturing technologies, DLP, LCM, and LIS. And with that, we will actually now move into the bulk of the webinar. So welcome once again, everyone, and let's get started. I think we're all muted.
Oh, yeah, sorry, I was unmuted. I was controlling the different things, so sorry for the short problems. So thank you again for the introduction. Also, very warm welcome from my side. I'm happy to have you here today. We want to introduce you into the LIS or LIS technology, as we can also call it, the new way of 3D printing. Before we get starting, please let me introduce a little bit to Lithoz for those people who don't know us yet. So basically we are, I would say, very well known in the field of ceramic already, because we are very clearly the market and innovation leader in ceramic 3D printing, especially when it comes to high performance ceramics. We are offering a full solution of printers, materials, software, and also a lot of customized solution. Just to give you a number, we are nearly 120 employees at the moment at 4 locations, 2 in Austria, 1 in the United States, and 1 in China. And we have far more than 100 machines installed worldwide, whereas what I'm actually very proud of, to have 25% of our customers have more than 1 machine, which is actually quite a high number. We have been one of the pioneers in the field of ceramic additive manufacturing and have really started from scratch more than 11 years ago. And just to give you also an idea of the market, I think that was it's really cool to see that although the ceramic additive manufacturing market is rather young, it's really growing now very, very fast, and we see this as well. So this is something which we can feel. We have in the pandemic, during the pandemic, we have employed more than 50 additional people, and so we really see this growth already. We have customers who are really using this as a production technology. What we do and what we have seen is that with the technology, which I will just show you in a second, the LCM technology, we are not capable of addressing the whole market. And so we decided to also introduce the LIS technology. But first of all, let me come to the LCM technology, which maybe some of you already know. LCM stands for lithography-based ceramic manufacturing, which means that we're using light as a structuring method. So very similar to stereolithography, to DLP-based technology. And what I dare to say in the meantime, that this is currently, our technology is currently the industrial standard for high-performance ceramics and is used worldwide, and also used as a production technology. So one of our biggest customer will produce 1.5 to 2 million parts this year with this kind of technology. I don't want to go into detail how it works. There are a lot of webinars and things where you can watch it and see an explanation for it. But I just to introduce you to LCS, I think it's important why we need LCS. Therefore, it's important to understand why we have LCM. So what we already have here is a very broad portfolio of different materials. What you see here, I mean, you see some dark materials, but most of the materials are rather not dark. They are white or whitish color, and this is one of the main drawbacks of lithography-based manufacturing, either DLP or SLA, that you cannot use all different types of ceramics, because light absorption is sometimes an issue, and you cannot absorb, or you cannot penetrate through the material because it absorbs too much light. One other issue where we can use LCM very much is to make very fine and delicate structures. So we can go down to 50 microns in strut thicknesses. And as you can see here, I mean, it always looks very big here if it's on the screen, but basically these are very small and tiny parts, and thinner than a human hair are these struts. And so this is, I mean, this is really the one very end, and definitely this lithography-based technologies, they are more used for smaller parts with thinner wall thicknesses, but there is definitely a limitation in the wall thickness, because we are using a photopolymer binder with a very high ratio actually, and therefore the binder burnout is difficult, and we cannot make whole wall thicker than maybe maximum 10 millimeters or so. So if you want to make bigger parts, you need to make thicker parts, and this is why we are going for the LCM technology. One other advantage what LIS cannot do, but LCM can do, is multi-material. So we can also do multi-material. We can do combined ceramics, metal, and also, if necessary, ceramics with polymers. So this is what we can really do here. I think I don't want to go into detail since we are talking here about the LIS technology. And this is our solution to make large and colored, especially dark ceramic materials. This is what we call the Lithoz way of big, because with our industrial standard technology, we cannot address all customers' issue. So once again, dark ceramics and thick walls, this is what is needed. And how can we address this? So we have, together with Alumina Systems, introduced the laser-induced slip casting. The technology we are using, or the name we're using, is this Vario Ceramax Vario V900. As you can see here on the right picture, this is a laser-based technology, and it's a solution to print, as I said, large parts and dark ceramics. But, and this is always for me very important, to full density. This is something which we are focusing on, to always deliver the same material properties as in conventional forming. And it's definitely very complementary to the LCM technology. So it is an additional solution for the ceramic market. And as I always, my impression is always, there is not one superior technology for everything, but you really have to choose the right technology for your application. I will go into the details again, but here just very briefly, we will see throughout the webinar how it works. So it's a very simple principle, but although a very sophisticated one. So we have a water-based slurry. which is very close to standard materials, so which are used for slip casting, for example. So this is this kind of material which can be used. And a laser over a scanning system, so driven over a scanning system, simply dries the slurry. So it's a casting, as we know from casting, water is dragged out by the gypsum mold, and here we are drying taking the water out by simply using a laser. Currently, we have the building envelope, which we have for this current machine for the V900. We have 250 times 250 times 290. This is not really huge in that terms, but it can make very thick walls, as we will see later on. But the technology itself is scalable. You can make it much bigger. This is just a first machine which has this envelope for the first time. So here you just see again the difference. One main difference is that we're using a CO2 laser which dries the slurry. There we're using light to polymerize it, and one time we are building upside down, the other one bottom up. And as I said, we are focusing here with the LIS technology on thick walls, on large volumes, to really build them up very fast. So we're focusing here on build-up speed. We can also make use silicon carbide. We can use ultra-high temperature ceramics, and all other dark ceramics can be used. But it is not as precise as we are used from the LCM technology, which is focusing on precision, on accuracy, on really parts which does not have to be machined afterwards. It can really, usually I would say 99% of the parts in the LCM technology are used without post-processing, without machining, and also from the repeatability and so on. I would really, it's already a standard technology in ceramic forming, so with very high reproducibility. You will see afterwards some examples, but here once again some differences. So we have with the LIS, we have a water-based slurry, which is close to slip casting, and this is, I think, also a good thing which we have now for the ceramicists, where you can also develop your own slurries much easier than with the photocurable system, because ceramicists are used to work with these kind of water-based systems. So I think this is one of the advantages here of these systems. And as I said, wall thicknesses can be much thicker and bigger. Precision goes down a little bit, but you can also have a higher solid load because it's just water-based, and rather low binder content at the end, because you are already evaporating the water and you're left with around 3% binder. So you can really debind very quickly. So if you want, say, you can also, there is no need for debinding because it's so little binding agent in there. And of course, as I said, the build-up speed is for us important, but not in terms of really in terms of volume. How much volume can you produce? And this is, you can use thicker layers here, building layers, and this increases a lot your building velocity. And as I said, you can also have colored ceramics and process them as well. Here you see some achievements. We have alumina. You can see let's say the most common material. We're achieving normal densities, so above 99% relative densities, comparable material properties as in conventional forming technologies. And from the part size, you see, I mean, these are bigger parts than we are used from LCM, and more important, to have much thicker walls here to be used. Those things are not possible with the lithography-based technologies. And here we've also done some first achievements with dark ceramics. We've used silicon nitride, which can also be processed by LCM, I have to say. But most important is that we can use here silicon carbide, so really the SSSC, so the sintered silicon carbide. And we have here already some first very good results, very promising. You can see here some parts in the upper down right corner. The first shot of the density was close to 99%. So this is something where we see a lot of new potential for using silicon carbide. And of course, also other non-oxides as well as oxides, and also ultra high temperature ceramics, it can be used here. Here you see also a microstructure that you see it's really dense. It's really a normal microstructure. And I'm looking now forward to the other presenters to give here a deeper insight into the LIS technology. And Dr. Wampas will now take over and present his part of the presentation. So I'm looking forward to having afterwards the Q&A session.
So thank you and welcome to our presentation from Alumina Systems. And I try to get the control. So I'll see if it's working. Yeah, it's not working. So maybe Iveta will maybe take the control. Ah, now it's coming in. Okay. So some words to the Alumina Systems Group. We are situated here in Germany and in the Czech Republic. And we were founded by Siemens in the 50s. So we have a very long tradition, and we have a production space here from actual 6,000 square meters and close to 100 employees. Since 2018, the company is owned by the advisory board and the management. And in Czech Republic, now we have it's close to 4,000 square meters and 84 employees. And so we purchased the Czech site in 2011 as a low-side production, low-cost production site. And the sales volume in the group is around 13 million. Our core competencies is we are a ceramic producer. We have the ceramic manufacturing in-house. So we are producing in the year more than 130 tons of alumina oxide and making components and parts out of that. And our core competency is to vacuum braze the parts together with metals. So I would say 90% of our products are combined components made from alumina and metal. So we are using here active brazing, passive brazing, glass soldering, laser welding. And since around 8 years, we are now in the ceramic 3D printing business, and started 8 years ago with a printer from Lithoz, and develop this field further on in the next years. So next slide. Okay, we are in the setup we have now. We have this Serafab laser from Lithoz 8500. And Johannes, you know, it's the number 2 in the world, and with that printer we are producing a lot of small and very precise parts. They are not have to be reworked, like already said before. And the newer printer we have is a printer from 3D Ceram with a construction field of 600 by 600 by 300 millimeters, where we can print very big parts or a lot of small parts on the printer. And one of the biggest or the newest developments we made is it's in our rings for the atomic layer deposition with a diameter of 380 millimeters, or the bigger one with 500 millimeters of diameter, but they are not printed in one part. They are printed in segments. So every ring is made of 8 segments, what is then glass brazed together to a ring. Yeah, and the newest printer we have in house, this is always the same picture you have seen in the presentation of Johannes. It's the Keramax Vario V900, and as he already said, this is a system that works with a laser, where the laser tries the or evaporates the water out of the slurry. And this method is very fast, so we can speed up here from 400 micron to 1 millimeter of layer thickness. What is it's 20 times higher than a normal LCM method. And this is the printer where we start now to make big parts with a bigger wall thickness, and or even big components if we have a bigger platform. Yeah, if you compare the both systems, you have the normal system, the LCM system for 3D printing. You have a binder content from very 50 volume percent. And for the LIS process, you have a binder content of only 2 to 3 volume percent. And this leads to a limitation in the wall thickness, what we see by 6 to 8 millimeters. And for the LIS process, we have already achieved wall thicknesses bigger than 20 millimeters. And one disadvantage of the LCM process is against the LIS, that we have a two-step process for debindering and sintering, what leads us to 5 to 6 days for debindering and 2 to 3 days for sintering. And in the LIS process, because the slurry is very similar to our slip casting masses or our pressing powder, we have only a one-step process with a process time of 2 to 3 days. And in addition, we can use standard temperature programs on the shop floor. This is very easy for the people they work with that. We don't have to teach them to take different programs for the kilns. And the next advantage is that we can use standard manufacturing machines for post machining, for green machining, and after sintering, of course, for the grinding if necessary. So this all leads to a short time to market for the LIS process, and I want to show that in the next slide. Here you see if you compare a normal standard process like we work now with and in the lower part and in the top you see the process with a LIS printing. If you add this to your standard process, if a customer comes and says, okay, I want to have 4 bigger parts, and this is can happen, it is more than normal, then we have to say, okay, we have no pressing form for that. We have to order him, we have to offer him a tooling, and the tooling leads to a delivery time of 8 weeks and costs for the tooling of around, let me say, 4,000 euros. And then the customer has to pay 4,000 euros, and we need 2 months just to make the preform. If you go to the LIS technology, you can start immediately to print the raw parts. And as I said, you are ready in 2 to 3 days. Yeah, you have to sinter it, and or if you want to green machine it, you are even better than 2 to 3 weeks. If you are placed on the machine and you can start at once, you are faster than 2 to 3 weeks. You are in 1 week, you are ready. And then after that process, first when you have the raw part, you can start with the machining, sintering with a standard process. And this brings you at least 4 to 6 weeks of advantage, and the customer has not to pay for any tooling. And this is all just referred to the construction size of the printer. The bigger the printer is, the bigger parts you can make. Here I have added some pictures from our production, and this is what I just mentioned with the isostatic form. What you see here is the jacket housing of the isopressing form and the metal core. And if you have to buy that, is around 4,000 euros. This form will be put in an isostatic pressing with 1,800 bars. And what you get out, you see on the next slide. Yeah, you see this blank. This is the isostatic pressed tube. Like the ceramic people say on the left and the right side with that elephant foot, and then you have to put that in a green machining, and then you get out this machined green raw parts, and this is what you get from the direct from the LIS printer. So this tube, what you see here in the second picture on the left side, is the raw part. You have to machine it and then put it on a transferred platform for the kiln, and then in the gas center furnace. Yeah, what we have done already, we have printed some cubes. This is for 3D oriented people. Normally, nothing magic to print a cube, but to print a cube with a 20 millimeter wall thickness, this is something new. So this is a very simple example what is possible with that new technology. And like Johannes mentioned before, we end up at the 3.93 density. So this is not that is a material where you can work with, where you can make constructions with. So here you see some examples where we see the potential for raw parts we can print with that machine. Coming to my summary, yeah, with the LIS technology, we are able to make big and very thick-walled components, and we are able to make the machining and the post-machining with standard machines on the green bodies. By the way, then we are very fast by printing, and we can use standard sintering programs and all the machines you use in the standard manufacturing process. The materials we have in focus is clear. We are working mainly with aluminum oxide. But we have some things or some R&D projects for cordierite or for silicon carbide, and yeah. So I hand over to the next speaker.
So, yeah. So thanks, Mr. Wambers, and hello, everybody. Yeah, I will close the lecture series with insights into the technology development of the LIS process. Therefore, I will introduce the printing process flow, some words to the LIS technology today and tomorrow, a basic insights into the material development and the advantage of the LIS technology from our point of view. At this point, short words to who we are, what's our background, and what we're doing. Yeah, we are QEP3D, founded by Manja Sebe and me in February this year. We are located in the Green Park, Stahnsdorf, close to Berlin. The technical part of QEP3D has more than 14 years experience in the field of slurry-based ceramic printing, with some inventions, patents, and publications. Manja has more than 16 years experience in all fields of economy. And in our point of view, it was a perfect team to start up. We're focusing on water-based ceramic 3D printing processes, and there are further development. One of them is, of course, the LIS process. And what we do is to consult and support you or customers to the right printing process for the applications. We manufacture components, we carry out material development, prepare customer materials for the 3D printing processes, and adapt the process to the materials. If a standard printer not fulfill the customer requirements, we can customize the printer and process for their requirements and applications. And finally, we can support you to implement the 3D printing process in your production or company, including post-treatments and all other necessary things. So enough to us. Let's move on to the process flow of the LIS method. Yeah, apart from creating the 3D data and uploading the STL file to the machine, the preparation of the printing process in our house always begins with the preparation of the material. For the material processing, the ceramic powder, binder, and some additives are processed into a water-based suspension. The suspension is deposited layer-wise by a dispenser unit onto the build platform and subsequently is moved by a doctor blade. In order to write the component information into the suspension, a laser selectively dries out the suspension, and yes, and the layer deposition and writing the information into the suspension is an alternate cycle. After the build process, the part can be easily removed out of the untreated suspension. After drying and any necessary green processing of the components, it can be sintered like a conventional manufactured part. Yeah, to get a better visual image of the process, I will show you a short video. Let's start. Okay. The suspension is deposited onto the build platform, and the doctor blade smooths the layer. And the laser evaporates the water selectively and writes the part information in each layer. So the platform is moved out of the construction space and the component is simply removed or demolded out of the suspension. Here's some quarters, which was really fast printed. Okay, what can this technology already do today? Next slide, come on. It's not now. Sorry about this, but it will not step to the next slide. Okay. Sorry about it, but no, I got it. Okay, the biggest building platform today has the size of 200 to 250 millimeters, and we can achieve a minimum wall thickness of around 3 millimeters. Okay, because of the laser wavelengths and the water-based suspensions, the process works for oxide and non-oxide ceramics. Doesn't matter if black or white. Depends on the layer thickness and the process parameter. A build-up rate of around 10 millimeters per hour can be achieved at the moment. This technology tomorrow. Yes, one of the further steps is to scale up the build platform up to 500 to 500 millimeters, which opens higher part size or 4 times more parts within one printing steps. And yes, as Mr. Wambos has already mentioned and shown, it's possible to produce simple geometrics for green body post-processing very quickly with this LIS process. That's a big benefit compared to conventional production to get toolless, quick a green body. But on the other hand, to print very close to the final contour will reduce the post-processing steps of green body shaping and also saves material. Therefore, our development is in the direction of improving the resolution with thinner layers, special additives, and so on. And finally, to improve the build-up rates, we work at the laser and the scanning parameters. Now a few words about material development. Material development is always the interaction between suspensions and the process parameters. On the one hand, there is always a connection between particle size and the possible layer thickness. The layer thickness always depends on the viscosity and the surface tension of the suspension. The resolution of the process also depends on the layer thickness, but also on the particle size distribution, particle shape, and filling degree, and so on. Yes, that sounds a bit complicated, and it is. But the production of conventional slip casts, casting slips also requires years of experiments. But now the good news, in principle, all ceramic materials can be processed to a suspension with the right properties, and the process can be adapted to this suspension. So we are working on standard suspension filled with alumina oxides, silicon nitride, silicon carbide, and so on. And this means for you that materials will be available and you can do fundamental tests or prototyping on the LIS process. So, and in summary, the advantage of the LIS process and water-based ceramic suspensions. All ceramic materials can be processed regardless of their chemical compositions and particle size. Water-based suspensions are almost binder-free or organic-free. Therefore, an additional debinding step is not necessary, and there is no upper wall thickness limit. And with increasing the resolution of the process, very complex structures will be possible in the future. So, and compared to other suspension-based 3D printing processes, the material is quite cheap. Finally, I go into a few components made of different materials. Video is always a beautiful thing when it's work. And here is the molding step of a rotating gear made of aluminium oxide, and it will come back to you in the next slide. Yes, it works. So in principle, all shapes can be mapped. On the left, the molded hollow block. In the middle, the hollow block already dried and ready for sintering. And on the right, this rotated gear. The components are already very close to contour and just require little or no green processing. The silicon nitride part shown here is one of the first tries of silicon nitride suspension on the LIS process. The process parameters and the suspension were not optimized. Nevertheless, this geometry could be manufactured quite precisely and sintered without cracks. With this technology, basic tests have already been carried out with aluminum oxides, silicon carbide, silicon nitride, and various porcelains. So we are ready for the LIS process. Are you too? Then walk me ways. Thanks for your attention, and back to Madeline, I guess.
Yes, indeed. Thank you. Thank you, everyone. And well, I see we have quite a lot of questions already, so we can get into it. We will answer as many as we can. Afterwards, you can always as well get in touch with Lithoz to have, or anyone to have your questions answered as well. But let's get to it. So the first question is, why are you not using a huge SLA machine to produce either big ceramic parts or multiple small parts? Are big machines more productive? So a complicated one to start.
Yeah, I think this maybe this addresses to me. So I think two important things which were already mentioned. The one thing is I'm thinking that you always have to have the right technology for the right application. And these lithography-based technologies are more focusing on smaller parts, or are better for smaller parts and thinner walls. So big machines usually tend to make big parts. And as we have seen in the presentation of Alumina Systems from Holger Wampers, is that he has a perfect part for example, for bigger machines, but basically they can also not do everything. And I think one really misconception is currently that bigger machines are working faster or more productive, which is actually not true. So we have a very good understanding of the technologies, I would say. I think that the best understanding in the market, because we are using a lot of technologies in-house, which we are just using for our labs and not selling it publicly. And so we can evaluate all those things very good. And we think that if we really talk about lithography-based, or in really making parts without machining afterwards, without afterwork, I think the LCM technology as we have it is really, and we see this is the industrial standard and can be used also for huge batches or for huge sizes in terms of numbers of parts. And the LIS technology is really something which filled a gap for the ceramic industry in terms how to apply it to other applications, other materials.
Great, thank you so much. That was a very complete answer. Well, as I mentioned, I'll go with what's been upvoted, but just to keep with a similar theme, what exactly happens when the laser hits the suspension? Could you please explain it in detail?
Oh, yeah, this is, I will explain this. This is my part. Iveta, could you please go to the backup slides? I prepared something for this. Oh, okay, thank you. So usually you have to think about that the LIS process is more related, or you can compare it, for example, with a casting in a plaster mold. So what you need is, for example, here is the powder, the water, and the additive. You mix it together to a slurry, and the shape, and you bring it into shape into the plaster mold. Yes, I can do. So, and you put the slurry in the plaster mold and wait a certain time if the wall thickness is high enough. After that, you have the drying process and you get to the components. So the LIS process is a little bit similar. So we have the powder, the water, and the additive. You get into the slurry. So that is more or less the same slurry composition you can start with. But now you do the shaping of the component by the laser. So you dry, here you dry with a plaster mold, and in the LIS process, you do it with a laser process. And afterwards, after drying as well, you have the sintering and the component. The next slide is what we start with. So you have the component, the component build-up. So you have a container, which is where you have the slurry in, the building platform. And on the building platform, you have the laser, as Thomas Mueller showed already in his short film. But what happens now directly under the laser? So at the beginning, you have here, we have the reaction here in a volume element. And you have here the filler elements, the filler particles, the water, the additive, and some binder materials. And under the laser is the reaction zone. And now we start, what happens now when the laser evaporates the water. Second, now it's going on, okay. So when the laser evaporates the water, you get out of this element, of this volume element, the water out. So the particles move next to each other, and according to the binder and different additive, they start to stick together. And they so they contact next to each other. And if you do this for several times, so a longer dwelling time of the laser or a number of crossings lead to greater penetration of the depth of the layer. So you see the increasing of the layer height is now here increasing. And now we move on and to evaporate some more water. And here you can see you have here a very, very high layer built up. And when you see here the penetration depth, we can here achieve a depth of height up to 500, sometimes also 1 millimeter can be achieved. And with the penetration depth in the polymer-based slurs, we can only achieve here something around 25 up to 50 microns. Okay.
Great. Okay, well, thank you. That was very informative. Extremely interesting. And moving on to the next question for whoever would like it. Takumi asks, have you ever printed silicon oxide-based ceramics like core in the LIS process?
Is it the question to me?
No, I don't know.
Maybe. Silicon oxide, yes, we printed. Not with this machine, but with the basic equipment at the TU Clausthal. A few years ago, we have developed a simple slurry composition. And yes, it's possible to print with a quite good resolution.
Good. Well, then next question as well is, can the leftover material from a print be reused? If yes, does it need filtering and cleaning? And what percentage of this leftover material can be reused?
At least a fast answer, yes, it can be reused and does not need any filtering. It's slurry can be just reused.
Great, well, that makes it easy. Well, continuing on the theme of materials, another anonymous attendee would like to know, are there any medical grade materials for LIS technology?
In principle, you can use, I think that's the good part of this technology, you can use any material here, and they could be also medical grade. I mean, ceramics are usually bio-inert or even bioresorbable, whatever you need. But so far, we have not yet worked on medical grade materials for LIS.
I think this question relates more to hydroxyl apatite.
Okay, yeah, but
related materials. So, but this is, of course, yeah, that's correct. Yeah.
Okay, so possible, though we haven't done it. Actually, a question just became popular. Another anonymous attendee would like to know, how does the LIS what is the benefit of using the LIS technology over binder jetting for ceramics?
Thomas, would you like to?
In principle, binder jetting, with the LIS technology, you can use all particle size. Yes, for the standard binder jetting, it's just possible to use particle size down to 20-25 microns. And also the density of the powder bed is not comparable to the LIS technology or to the LIS screen bodies. So with the binder jetting, it's more or less not possible to sinter a dense ceramic. With the LIS technology, it is possible.
This was for us one of the key aspects why we were using LIS technology, because if you do high performance ceramics, you want to have a dense part, and this is, besides reaction bonded silicon carbide, not possible with binder powder jetting.
Exactly.
So
Sorry, I was muted. At least Zoom told me. Whoops. Well, is it a webinar? There are a couple of times that we have that. So next question is, can parts in the they said LCS, but I think they mean LIS process be stacked on top of each other like nesting in an LPBF process?
You mean a 3D? Basically, you cannot. You need support structures to nest it in the LPF process, and I think since it's not self-supporting, it's not possible.
Okay. Yeah, well, makes sense. Another question which has gained suddenly in popularity is, what are the max and minimum viscosities of the slurries that can be used in the LIS process?
Maybe a question to us.
Maybe
okay, yeah, sure.
I don't know any viscosities by value right now, but once again, we are using here standard slurry. So this is it's the same slurry we are using for a slip casting process. And so I cannot say by heart now what is the viscosity exactly, but it's nothing special. So you just mix your slurry together, and as you use it for slip casting, you fill it in the printer, and you can print with that, more or less.
We simply don't know yet the limitations, but I'm totally agree. You can use anything. It's not of very importance.
Well, we'll stay tuned in any case. A lot of questions on limitations, so we shall see. Another question is, what is the thinnest wall thickness you can print with? And have you seen any warping when thin part printing?
I think Thomas, you
Yes.
mentioned this already in your presentation.
Yes, the absolute minimum wall thickness is maybe 3 millimeters at the moment, and it's also because of the layer thickness. Yes, with a layer thickness of 500 microns or 1 millimeter, it's not possible to achieve really thin wall thicknesses. So that's the reason for why we go or try to go down with the layer thickness and to achieve a smaller wall thickness. But it's also a point of the slurry or the particle size distribution and the particle form and so on, because it has to be stable enough to build up 3 millimeter wall thicknesses. So, and yes, maybe in the future it goes less, but it was not the point to go with this process to really thin wall thickness. We want to achieve thick wall thicknesses, and everything else can be post-processed by green machining.
And actually, since we just talked about post-processing, well, not exactly, can green parts with a low percentage of binder, I think that should be stored for some time and sintered after a number of days and weeks? If yes, what would be the storage conditions?
Yes, it could. So usually after you have print these parts, you have to dry them in a furnace, 40 degrees, something like that, quite slowly. And after that time, you can store them for weeks or at least a month or two. And you should take care that the the part should not soak once again water into the body. It should be dried, stored at least.
That would make sense, as it would with similar. And actually, gentlemen, are you able to stay a few minutes over to answer one or two more questions? Great. Well, hopefully you can stay with us. If not, well, we'll put up the recording later. Also, feel free, actually, if there's a email address that people can reach you for questions, if you could just put it in the chat, do feel free to reach out if you have specific questions. Well, since we were just talking about slurry, an anonymous attendee is asking, how do you wash out the residual slurry after demolding?
Thomas, maybe. Are you muted?
I have a problem with muting, and I did get the question. Could you?
No, I can answer. I can answer.
Okay, sorry, thanks.
You just take out the part of the as it's seen in the video, and then you maybe rinse it with water, and that's it. So
Easy.
it's very simple, yeah.
Yes.
Yeah.
If it's the answer, yes, it's.
Yeah.
It is.
Well, good. A fast answer, so we can get more questions in. What density, if you know, have you achieved with SiC?
With SiC, we were close to 99%. So, but it was really the first sintering procedure. So without any optimization, I guess we will achieve the normal, so to say, normal material properties as we've achieved with aluminum and with other materials.
Good. And actually, so a question addressed for Dr. Holger, actually, not exactly LIS, but what is the accuracy you are getting with LCM? If you could just unmute yourself, please.
Sorry. Pardon, I didn't get the question.
Yes. So what is the accuracy you are getting with LCM?
The accuracy?
Accuracy.
Yeah. Accuracy, okay. We can, in the moment, we get about 60 microns. 60 to 70 microns of tolerance. And this is only referred to the light source. But this is the printer. And Johannes, maybe you can comment that again. The printer is now 7 or 8 years old. I think the newer printers they are even going down to 60 or less microns.
Yeah, I mean you are now referring to the resolution of the printer. So the printer you currently have has a resolution of 60 microns. But in terms of accuracy, I would say even with these printers you could achieve less than that. Our standard accuracy is in the range of 10 to 20 microns of repeatability. But we have also customers which are focusing very much on specific parts, which even go below 10 microns in accuracy.
Excellent. Another question is asking, what is the binder that is used?
We cannot answer.
Similar to sleep casting slurries.
Yes, something like this.
And then just a couple more. What would you say is the max thickness for something for alumina and dark ceramics?
In terms of wall thickness?
Yes, I imagine. They don't specify, but
yeah.
I understood.
In Holger, what did you already achieve in terms of
Now we are for alumina we are more than 20 millimeters, and for silicon carbide we have no expertise right now. This is only the first trials you did in your house, so I don't know what you.
I think yeah, as I said, 20 millimeters is the current status, but I don't think that this is the limit.
Yeah,
we just have not explored this to a big extent.
Yeah, the parts comparable to conventional manufactured parts. So take this wall thickness and around this is the limit.
There you can, if you, what we have not have in consideration right now is the sintering process as well. As you know, we have standard processes for wall thicknesses till 20 millimeters maybe, and if we have even thicker parts, maybe to 40 or 50 millimeters, we have already produced. We have sintering programs. They are double as long as that standard processes. So the wall thickness is not only limited by the printer, it's also limited by the sintering program. So this is you have to see in combination.
Yeah, but the limitation doesn't come through the 3D printer. It's more from, let's say, pure material science at the end.
Yeah.
Yeah. And then this might be a good last question. Are you able to give estimates for cost per part?
It's absolutely.
It depends on the volume and the shape and the design.
Exactly. Exactly.
Depends on a lot, in which case I will end with one last question because I think we should wrap up. What would be considered a standard temperature program on the shop floor, and what is the debindering sintering temperature in that one-step process?
The debindering temperature is about 1000 degrees C, and the top temperature for sintering is around 1650 degrees C. And of course, we have our own sintering curves, how we do that, and in what time and which stiffness we go up to the temperatures. But the two levels are around 1000 till 1600 to 1000, and for debindering, and 1650 for sintering.
Great. Well, with that, I think we've gone quite a bit over, so I'm going to say goodbye to everyone. Thank you so much for coming. Do feel free to get in touch if you have specific questions. If there's a contact info, if you could just please put it in the chat. Thank you very much, gentlemen, for being with us today. It was very interesting. Well, it was fantastic. Thank you so much. And well, thank you everyone for coming as well, and have a great rest of your day, afternoon, depending on where you're located.
Thanks a lot.
Okay.
Bye.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.